So in this chapter, we'll be going over and reviewing questions that pertain to acid-base chemistry. And so we'll start off with question 10.7 from the book. And it is asking us here to identify the Bronsted-Lowry acid and bases in reactants in each of the following reactions. So we'll look at both A and B. And so in this case, in this question, you want to remember that by definition, a Bronsted-Lowry acid is one that will donate an H plus, or an acidic proton, and a Bronsted-Lowry base will accept it. And so here, what we're looking at overall is which reactant is losing the H plus. And so here you see HI going to I minus. And so HI going to H plus and I minus. And so HI is the Bronsted-Lowry acid. And then as far as a Bronsted-Lowry base, a Bronsted-Lowry base is a proton acceptor. And so we're looking at which one gains an H plus. So here we see H2O and go into H3O plus. So H2O must gain an H plus in order to become the hydronium ion. And so H2O is the Bronsted-Lowry base, and HI is the Bronsted-Lowry acid. We can look at B, and so in B we're looking at again, Bronsted-Lowry acid is going to donate the H plus. And so we're looking at which one is losing the H plus, and so here we see H2O going to OH minus. And so H2O, in order to go to OH minus, must donate the H plus. And so that will be the Bronsted-Lowry acid. And a Bronsted-Lowry base will accept a proton. So F minus gains an H plus to become HF. So F minus plus H plus goes to HF, and that will be a Bronsted-Lowry base. In 10.9, we're being asked to write the formula and the name for the conjugate base of each of the following. And so we'll look at, we can look at A. And so a conjugate base, all right, is going to have one less acidic proton. So HF will lose an H plus and become F minus, or the fluoride ion. And so F minus is the fluoride ion. And B, H2O, if it acts as an acid, it's going to make its conjugate base. If it loses an H plus, you'll be left with an OH minus. And the OH minus is called the hydroxide ion. And then we'll skip to D. D, HSO4 minus. If it loses an H plus, it's going to be left with an SO4 minus 2, and that's the sulfate ion. And so that's what 10.9 was asking us to do. In 10.11, it's asking us to do something very similar. And so we'll just do a couple of these. We'll just do B and C. And so B, if we want the conjugate acid, that means we're going to have to gain an H plus. So H2PO4 minus will gain an acidic proton to become H3PO4. And that is phosphoric acid. Oh, I guess I skipped. That was supposed to be for letter C. And then going back to B, if we have H2O, that gain an H plus, that's going to make H3O plus. And that's the hydronium ion. And 10.3 is asking us to find the conjugate pairs. So a conjugate pair are only going to differ by one acidic proton. And so we have two conjugate pairs in each reaction. And so we'll have the carbonic acid becoming HCO3 minus, and then the H2O with the hydronium ion. In B, we'll have the ammonium and its conjugate pair to be the ammonia, NH3. They only differ by one H plus. Same thing here with the water and the hydronium. They only differ by one H plus. And so that's what you'll have to do in questions like 10.13. And 10.23 is asking us to predict whether each of the following is going to contain mostly reactants or mostly products. So we'll just look at A and B. And it asks us to look at table 10.3 to help assist us in figuring this out. And if we look at A, we have carbonic acid, H2CO3. Carbonic acid is a weak acid, and a weak acid has a strong conjugate base. And so if it's a weak acid, we're not going to dissociate very much. We're not going to make very much product. And so here in A, we're going to have a little go in this direction, but more so in this direction. And so we're going to have mostly reactants. And that's based upon being carbonic acid being a weak acid. In B, we have ammonium and we have ammonia. And ammonia is a weak base. And so if it's a weak base, it's not going to go much in the reverse direction, very little in that direction, and more in this direction. So, because a weak base has a strong conjugate acid, and so this ammonium will dissociate more and go back toward the product side, and ammonia is a weak base, and so it will not make much in the reverse direction. And so this case in B will be mostly product. And so that's what you'll have to do with questions like 10.23. The next one we'll look at is 10.25. And so we're going to be comparing these two reactions. And so we have the H2SO3 reaction and the HS minus reaction. And then we're also given the Kas, the acid dissociation constants. And so in A, it's asking us which is the stronger acid, H2SO3 or HS minus. And so what we're going to base this solely upon is the Kas. So the Ka for the H2SO3 is 1.2 times 10 to the minus 2. HS minus is 1.3 times 10 to the minus 19. And so whichever has a larger Ka has produced more product, and so dissociates more, and so is a stronger acid. So whatever Ka is bigger is a stronger acid. And so H2SO3 is a stronger acid. In B, it asks what is the conjugate base. of H2SO3, and so that will have one less acidic proton, and so HSO3 minus is its conjugate base. C is asking us which acid has the weaker conjugate base. And so acids and conjugate bases have an inverse relationship in terms of strength. So a weak conjugate acid will have a stronger conjugate base. A stronger acid will have a weaker conjugate base. So whichever one is the stronger acid has a weaker conjugate base. And so the acid that has the weaker conjugate base would be the H2SO3 because the Ka is bigger. The Ka is bigger means it's a stronger acid. A stronger acid has a weaker conjugate base. And then which acid produces more ions? And so if you remember, Ka is equal to products over reactants. And so the products are the ions. All right? And so the one that will produce the most products will produce the most ions. And so whichever one has a larger Ka will produce the most ions. And so in this case, again, H2SO3 will produce the most ions because it's a stronger acid. And 10.33 is asking us to indicate whether each of the following is an acidic, basic, or neutral solution. And so what we'll look at is look at these conditions. If the concentration of H3O plus is greater than 1.0 times 10 to the minus 7 molar, that means it's acid. If H3O plus is less than 1.0 times 10 to the minus 7, it's a base. In terms of OH minus, if OH minus is greater than 1.0 times 10 to the minus 7, that means it's a base. If the OH minus concentration is less than 1.0 times 10 to the minus 7, it's an acid. And so in A, we have H3O plus that's greater than 10 to the minus 7, so that's acid. And in B, we have it less than 10 to the minus 7, so that is base. Remember, we're dealing with negative exponents, so it's not maybe confusing because of that. So because if a negative exponent, if you have a smaller negative exponent, it's actually a larger number. Here, OH minus is equal to 8 times 10 to the minus 3 molar. And so that is greater than 10 to the minus 7 molar, so that is a base. And 3.5 times 10 to the minus 10 molar is less than 10 to the minus 7, and so that's going to be acid. Now we'll move on to 10.35, and 10.35 is asking us to calculate the H3O plus concentrations with these given OH minus concentrations. So in these questions, we'll have to use the idea that Kw is equal to H3O plus times OH minus. And that is equal to 1 times 10 to the minus 14. So in A, the Kw is equal to H3O plus times OH minus. Since we are looking for H3O plus, we can rearrange the problem by dividing both sides by OH minus. And so that would give us Kw is equal to, Kw over OH minus is equal to the concentration of H3O plus. And so in this case, we have 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 9. And we get a number of, plug it into our calculator, and we get 1.0 times 10 to the minus 5. We'll skip B and we'll go to C. And C we have, we'll just start with Kw over OH minus equal to H3O plus. And we get 1.0 times 10 to the minus 14 over 2 times 10 to the minus 5. And so when we do that, we get 5 times 10 to the minus 10 molar. And then the last one, we'll look at D. D, again, we'll start at Kw over OH minus is equal to H3O plus. And that gives us 1.0 times 10 to the minus 14 divided by 4.0 times 10 to the minus 13. And we get a number of 0.025 molar. And so that's how you convert from OH minus concentration to H3O plus concentration, which is going to help us in the next problem. Which is 10.41. And let's see. Try to focus this in a little bit. Seems like it's there, a little bit better there. So here's asking us to calculate the pH of each of these, of each of the following. So we'll do a few of these. Won't do them all. And so we'll look at B. So B, our pH is equal to the negative log of H3O plus. And so this one is pretty much just plug it into the equation. So we get a negative log of 3.0 times 10 to the minus 9. And so the real trick of this is just being able to make sure you're plugging it into your calculator correctly. And so we get a number of the log of 3.0 times 10 to the minus 9 is negative 8.0 8.5229. We'll just round it off there. And so we get 8.5229. And to figure out how many significant figures we're allowed to report, since we have two significant figures in the coefficient, we're allowed to report 2 decimal places. So it's equal to 8.52. In C, I will just skip to D. It's a little bit tougher. So in D, we have the OH minus concentration. So here we need to do 2 steps. First, we need to get in terms of H3O plus, and then we can figure out the pH. So remember what we did before, Kw over OH minus is equal to H3O plus. And so we get 1.0 times 10 to the minus 14 divided by 2.5 times 10 to the minus 11 will give us the H3O plus concentration. So that's the first step. And we get 4 times 10 to the minus 4. And then we can go on to the next step. pH is equal to the negative log of H3O plus concentration, which is equal to the negative log of 4 times 10 to the minus 4. And we get a number of negative log is equal to, bumping the negative log of, oh, nope. So we get a negative of negative 3.9, messed up again, minus negative 3.398, we'll say. And so that gives us 3.398 with the negative and the negative. And so again, we have two significant figures in our concentration, so we're allowed to report a pH of with 2 decimal places. So we get 3.40. And so hopefully you'll be able to see that, even though the screen is moving back and forth from me bumping into it. So that's how you do B and D. So the next one is a table that's similar to one of your homework questions. And so here you're given this table and you need to go from one side, fill in the blanks basically. And so in the first row, we have an OH minus concentration of 1 times 10 to the minus 6. So in order to go to H3O plus, remember that Kw over OH minus is equal to H3O plus. And so 1.0 times 10 to the minus 14 over 1.0 times 10 to the minus 6 gives us 1.0 times 10 to the minus 8. So we put that in our chart. So pH is equal to negative log of H3O plus. H3O plus was found to be 1.0 times 10 to the minus 8. And so that gives us a negative of negative 8. And so we get a pH of 8. And if this is acid, basic, or neutral, it has a pH greater than 7, and so it must be basic. In the next row, we have a pH equal to 3.00. And so if we have a pH of 3.00, then the H3O plus is equal to 10 to the minus pH. And so 10 to the minus pH, it would be 10 to the minus 3. And so we get 1.0 times 10 to the minus 3 for H3O plus. For OH minus, we do Kw over over H3O plus will give us OH minus. And so we get 1.0 times 10 to the minus 14 over 1.0 times 10 to the minus 3. And that will give us a value of 1.0 times 10 to the minus 11 for the OH minus. And if this is acid, base, or neutral, pH is less than 7, and so it must be acidic. And so that's how you'd fill out the table like this. In 10.49, it's asking us to balance the neutralization reactions. And so we'll look at A. We have HCl and MgOH2 making MgCl2 plus H2O. You can approach this question in balancing in different ways. One way you could look at it is that you need to have the same number of OH minuses as acidic protons. Or you could just look at it and balance it as we've always done. So here what you can look at is you have Cl2. You have two Cl's. You only have one on this side. So you can put a 2 right here. And so then you can look at, make sure you have, so here you see you have 2 O's, but you only have one here. So you put a 2 in front of there. So now we have 2 chlorines on both sides. We have 2 oxygens on both sides. We have 1 Mg on both sides. And we have 1, 2, 3, 4 hydrogens. And 2 times 2, which is 4 hydrogens. So we are balanced now. We can look at B next. We have H3PO4 and lithium hydroxide making lithium phosphate, Li3PO4, and water. Remember that neutralization reactions, you always end up with water and you always end up with a salt. So here you have 3 Li's. Here you only have 1, so you need to put a 3 there. You have 1 phosphate group, and 1 phosphate group. That seems fine. You have 3 acidic protons reacting with 3 OHs, and that would make 3 waters. So let's just double check everything. So we have 3 plus 3 hydrogens, so that's 6 hydrogens, and 3 times 2, which is 6 hydrogens. We have 1 PO4 group. We can just keep that PO4 group together because it doesn't break apart. We have 3 lithiums. And let's see, we have 3 oxygens here. And then 3 oxygens, came off there, and then 3 oxygens here. And so we look pretty balanced. And so that's how you would balance a neutralization reaction. And then the last one, 10.51, we're asked to predict the products and write a balanced equation for the neutralization reactions. And so in A, we have H2SO4 and NaOH. In the neutralization reaction, we're always going to make salt and water. So we know we're going to end up with H2O, and then you just put the anion of the acid and the cation for the base together. You have NaSO4. We're not done quite yet. Sodium is a +1, sulfate's -2, so crisscross. So Na2SO4. And so here we have 2 sodiums. Here we only have 1, so put a 2 there. Here we would have 2 oxygens. Here we only have 1, so we'll put a 2 there. And that should balance us out. So we have to see, we have 2 plus 2, which is 4 hydrogens. 2 times 2, 4 hydrogens. 1 SO4 group. 1 SO4, 2 Na, 2 Na, 2 oxygen, 2 oxygen. The next one we'll look at is B. We have HCl and iron 3 hydroxide. And so that we're going to always make, with acid and base neutralization, always make water. And the salt that's left is going to be the metal with the non-metal. And so iron was +3, chlorine is -1, crisscross, Fe3Cl3. See, we have 3 chlorines, only 1 here, so we'll put a 3 there. We have, and then we have 3 oxygens here, and we only have 1 here. And that should balance us out. Let's double check. We have 3 plus 3, 6 hydrogens. 3 times 2, 6 hydrogens. 3 times 1, 3 chlorines. 3 chlorines. 1 iron. 1 iron. 3 oxygens. 3 times 1, 3 oxygens. And we're all balanced up. And so that's how you balance out these neutralization reactions. And again, you want to remember that when you neutralize acids and bases, you're going to make water and you're going to make a salt. And so those are questions similar to you that are found in your homework. And so hopefully these will help you in completing your homework correctly.